Check. Let's talk about lab 15, part 1, the push-pull buffer. So the push-pull buffer is a kind of a generalization. It's an improvement of the emitter follower that we studied earlier. So in fact, it is two emitter followers kind of connected toe-to-toe. So one of them is made with a conventional NPN transistor, the transistors that you're familiar with already. And so that actually follows the positive part of the signal. And then the other part down below, which is new, is made with a PNP transistor. So it's got this funny symbol where the emitter, instead of the emitter coming out of the transistor symbol, the emitter is pointing back into the transistor symbol. So the PNP part is another emitter follower, kind of upside down, and it follows the negative part of the signal. And a push-pull buffer, or push-pull follower, is often used as the output stage of an amplifier. It's often used where you want to amplify a bipolar signal, a signal that could be positive or negative, in a way where you want to provide a pretty significant amount of power to the output, but you don't want to waste a lot of power when the circuit is idle. So an ordinary emitter follower, you might remember from our earlier labs, in order to set it up to follow a bipolar signal, a signal that could go above or below zero, we had to have a resistor from the emitter down to a negative voltage. And the implication is that if the input at the base was sitting at zero, a significant current flowed through the emitter even when the circuit was idle. So this is sort of a drawback. It basically wastes a lot of, the quiescent power is significant compared to the useful power. So the push-pull doesn't have that drawback. We are building this not with our ordinary 3906 and 3904 transistors. We're building it with these high power transistors, the MJE3055 and the MJE2955, because these are rated for higher power. In a moment, we're going to use this to drive a speaker. So we want to be able to make a lot of noise with the speaker, so we're using a high power transistor. So instead of you might be familiar with kind of EBC for the transistors we were using for the earlier labs, the low power transistors, but instead the pinout here is BCE, so base collector emitter. And it's the same for the 3055 or the 2955. Also, watch out for this metal tab. It turns out the metal tab is connected to the collector. So you don't want to let the metal tab accidentally make a contact with something else. In particular, if you have the two transistors next to each other, the 3055 and the 2955, you definitely don't want the two tabs to touch each other because one will be connected to +9 and one will be connected to -9. You don't want to short those to each other. Okay, so let's think about what the circuit does. So we can draw an input waveform. So here we go. So here is voltage versus time. And then we can draw V in. Let's just make a sine wave like that. And I guess it might be useful to indicate a voltage scale. We'll do that in a minute. And so then okay, so for the positive part of the signal, our conventional NPN transistor will follow it. And you know if a transistor is active, then the emitter will be a diode drop below the base, and the output is from the emitter here. So we have to wait until the signal gets about a diode drop. So this output is basically flat here at 0 until the input gets a diode drop above 0. And then the output stays a diode drop below. So this distance here, this distance is, this is a diode drop, so it's like 0.7 volt diode drop. So then when the absolute value of the input signal is smaller than a diode drop, then the output is flat here. And then for the negative part of the signal, so a PNP transistor is like an NPN transistor, but basically all the signs are flipped. So then we have that so the input is the base here. So the emitter is going to be a diode drop above the base instead of below the base. And then remember in both cases, so here this collector is going up to the positive power supply voltage. This collector is going down to the negative power supply voltage. And I guess I only drew one cycle, and then it should repeat like that. Yeah, so then this would just continue onward. So you get these little flat spots where the absolute value of the input is smaller than a diode drop. And those little flat spots are called crossover distortion. So yeah, crossover. And you can hear that. So we will hear it in a moment. So the crossover distortion happens here. Okay. So and then of course this is a follower like any other follower. The purpose of a follower is to basically have the output voltage reproduce the input voltage. This does that except for this imperfection. We'll fix this imperfection with op-amp feedback in a moment. But the output current can be much bigger than the input current. So it's basically, you get much more power out than you put in. So this is why you can use like a fairly weak voltage signal, and we'll use it to drive a big loud speaker in a moment. Okay, so now let's take a look and see the version of the circuit we built. Okay, so I put the PNP transistor, the 3055, up above, which is handy because it's going to connect to plus 9 volts. And I put the 2955, the PNP transistor, down below, which is handy since it will connect to minus 9 volts. So remember, my convention is I use this red power rail for plus 9. I use this red power rail for minus 9, and I use this blue power rail for ground. So we have B, C, E. Actually, there are many ways you can build this, and actually I'll show you in a moment a photo of the first way I built it. But I decided that it's a little bit more, it's easier to show you all the connections when I separate the two transistors. Actually, I often put them right next to each other to make the whole circuit more compact. So the two bases have to be connected together. So that's done with this blue wire. So notice, right, so it goes across this little ridge in the middle. So this little blue wire connects the two bases together. And then the 3055's collector, that's the middle pin, goes up to plus 9 with this red wire. The 2955's collector goes down to minus 9. That's the middle pin here with this red wire. And again, watch out for these metal tabs. The metal tabs are tied to the collectors, so you don't want to let them bump anything by accident. And then the two emitters on the right-hand side are connected to each other with this little blue wire. And then I could pick either one. So then the emitters are wired to ground through this 1K resistor. So there's this 1K resistor. It's going from this emitter down to ground. And then we have the input signal is coming in on this green wire to the bases. So I can just go to either base and they're connected together. And then I have the function generator connected to this point, which I'm using for the input. And I have scope channel 1 connected to that same column monitoring the input. And I have scope channel 2 going over to the emitters monitoring the output. And then here, let me show you the alternate way that I built this. Okay, let me show you the alternate way I wired it up earlier. And then I decided that this was a little harder to show you. So I put the NPN transistor backwards. So instead of BCE, it's EBC. And then the PNP transistor here is BCE. right, so this was ECB. So then the two bases are connected together kind of automatically. And then I have, yeah, so that's right. And the place where they meet, the place where they overlap are the bases. And then I have the NPN collector in the middle with this red wire up to +9. And then I have the PNP collector in this middle wire with the red wire down to -9. And then the two emitters are on the outside. So this little blue wire is connecting the two emitters to each other. And I have this 1K resistor going from the PNP emitter down to ground. And then the input has to come into the bases. So that base area is kind of crowded. So this green wire is bringing the input into the bases. And then otherwise, the same thing is happening here in this column. So that's another way to do it. One danger of doing it this way is, again, if these two collectors touch each other, you'll have +9 shorted against -9, and you usually don't want that. But anyway, so if I have plenty, I mean, I often try to make the circuit compact and do it this way, but I decided to make it a little easier to follow instead today. Now let's look at the results in the waveform window. So the yellow curve scope channel 1 is the input signal. It's a 440 hertz sine wave, 2.5 volt amplitude, so that's 5 volts peak to peak, no offset. And then the blue or cyan curve is the output that's taken at the emitters here. And you can see the little flat spots, the crossover distortion as drawn up there on the board. So if the absolute value of the input voltage is smaller than a diode drop, then you get this little flat spot because neither one of the transistors is on. So we'll have a little trick to overcome that in a moment, although first we want to hear it and see, we'll see that you can actually perceive the sound. It gives you kind of a 1980s Atari game kind of sound. Yeah, so now if we make the waveform bigger, I have 1 volt per division on both waveforms, and I have ½ millisecond per division horizontally. So if I make the amplitude a little bigger, let me make it, let's go for, we could do 5 volts amplitude, I think. So that's 10 volts peak to peak. Yeah. So now the crossover distortion becomes less prominent with a bigger waveform because, of course, the 6 or 7/10 of a volt diode drop is smaller. It's a smaller fraction of the waveform amplitude, so it's not quite as noticeable. But I'm going to go back to what the lab write-up asked for. I'll go back to 2.5 volts amplitude, which is 5 volts peak to peak. Okay, now let's plug in a speaker and listen to this. Okay, now I added I put the speaker over here, but I put a 100 microfarad blocking capacitor between the push-pull output and the speaker. That's only because I have occasionally blown up speakers, not blown up, but I melted the wires of speakers by accidentally running a large DC current through the speaker. So the capacitor just kind of prevents you from accidentally running a DC current through the speaker. Although this capacitor our 100 microfarad capacitor is a polarized capacitor, so the capacitor itself can actually kind of blow up if you run a DC current in the wrong direction through it for too long. But anyway, there should be, as long as you just don't apply a DC offset. You should have no DC offset here, and everything should be fine. Also, don't put your eye right next to the capacitor. Or if you're kind of afraid of the 100 microfarad capacitor, because these electrolytic capacitors can blow up if you run a current through them in the wrong direction for a long time, then you could use the 10 microfarad plastic capacitor, and those are not polarized. Anyhow. Or you could leave out the capacitor, and the only risk is that if you have a big DC offset, you could burn out the speaker. So we have this. So here's the capacitor, okay, and normally it matters for an electrolytic capacitor which way you plug it in, but in this case we really have no reason to favor one direction over the other. So it doesn't really matter. And so one end goes at the point between the emitters here. Well, yeah. And the other end goes into the speaker. The speaker has two wires. It doesn't really matter which one is which. It's symmetric. So I used the red wire attached to the far end of the capacitor here, and then I have the green wire going down to ground. Be sure you connect this to ground and not to like -9 or something, because that will run a big, well, actually, no, it won't. Well, anyway, you don't want to do that. Yeah. So anyway, make sure you connect this to ground, not to like a power supply voltage. And okay, then we can go, I turned off the waveforms because the noise was annoying, so let me turn the waveforms back on. Okay, let's re-enable our waveforms. And okay, you hear A440, so that's also known as A4. It's the A above middle C. But it doesn't sound like a nice sine wave. It sounds a little bit like, it has that kind of sound of a 1980s Atari video game. Actually, kind of for good reason. I guess if we make the amplitude, oh, if we also look, so this is one place that's kind of interesting to monitor the power supply. So you see we have, where is it? It seems like this is like 100 milliwatts. Yeah, we have, I don't know, 50, maybe 100 milliwatts from each one of these power supplies. So now let's go, that was 1 volt amplitude. Let's go to 2 volts amplitude. It's louder. Oh yeah, it's kind of interesting to see. I don't really understand why it does this, why the output waveform sort of freaks out like this. Joe's might have an explanation. It's kind of interesting why it does that. I actually don't understand why it does that. And then you see we have about 1/3 of a watt, so well, maybe you can't see that, but it says about 300 milliwatts from each of the two power supplies, the plus and minus power supplies. And then I remember I had it set to 2.5 volts initially, even a little louder, and now I think it's about 1/2 a watt. Yeah, this is about 500 milliwatts from each of the two power supplies. And then here, I guess just for fun, so that is A4. We could do C4, it'd be 262 hertz. Okay, that's middle C basically. Okay, so that's, I'll go back to A440 since that's what the instructions ask for. Okay, and now I think I'm going to wire up an op-amp with feedback to get rid of the crossover distortion. You will both see that and hear it. Okay, I have wired up an op-amp follower here. And so for one thing, remember that you always need power for an op-amp circuit. So I didn't draw the power connections here. But you have to remember to connect pin 7 up to the positive power, and you have to connect pin 4 down to the negative power. So just keep that in mind. And so then the follower circuit, remember the follower circuit is kind of a degenerate case of the non-inverting amplifier. So the input goes into the non-inverting input, and then feedback comes from the output back to the inverting input just directly with a wire. You don't need a resistor for that. So remember, you should always look to make sure you see feedback from pin 6 back to pin 2 in some form. And actually, the way we've set this up right now, it does nothing at all useful. It just buffers the input signal before sending it to the base. So it's actually not, it's not doing anything useful for us, except maybe it's separating whatever the output impedance of the function generator is from the EE board from the input of the push-pull. But as far as we know, that doesn't do anything particularly useful. But we're going to see in a minute something really remarkable when we move the feedback. But in any case, we can listen to this. I think it shouldn't have really made any significant difference. It did change the waveforms in an interesting way. I'm not sure why that is. So let's see. We're going to Oh, hey, my waveforms app just crashed. I'm going to fix that. Okay, here we go. I don't know how that happened. So now I will enable my sine wave, and we can look at the scope. And yeah, the fuzz is gone. That's kind of interesting. There's still this funny shape, funny asymmetric shape of the push-pull output waveform, which I guess must be probably caused by like the reactance of the speaker or the capacitor. I don't know for sure. Be fun to explore sometime. But I don't think it sounds especially different. And so actually I went to 2 volts amplitude. I guess I had 2.5. I could do 2.5 again. That's what crashed. Okay. Okay, there's 2.5 volts amplitude. And the power supply, I guess that's fine. It's like 60 milliamps from each one. So it's half a watt from each of the 2 power supplies. We can go back and look at the scope. Okay. Anyway, so this is just a setup for the really interesting part. The interesting part has not happened yet. Let me just stop the wave gen. Okay. So now what I am about to do. Oh, by the way, let me just point out. So we set up this opamp follower, and then we took the output of the follower and connected it to the base here. Let's just point at that. So here's the follower. So we have pin 4 is going to -9 volts. Pin 7 is going to +9 volts. Feedback from pin 6 back to pin 2. We have the input. The input that used to go into the base is instead going into pin 3 here, and then we have this green wire, the output of the op-amp is going to the bases of the push-pull. So this this follower is not really doing anything yet. But now what we're going to do, this is the exciting part that you've been waiting for. We are going to take this feedback loop and we're going to move it. Here, I'll put it in yellow. We're going to take this feedback loop and we're going to move it all the way over to here, the output of the push-pull, just before the capacitor. And you know that negative feedback will cause the output of the op-amp to do whatever it thinks it needs to do to get these two things to be the same. That means it's going to try to make the push-pull output be the same as the original input signal. So that's going to be fun to see. Let's see that. Well, let's move the wire. Let me pause while I move the wire. So I'm reminded now, I hear clicking. I hear a clicking in the speaker every time I mess with the wires or turn the power on and off. I'm now reminded why I put this big capacitor here, and I'm also reminded why it's really a good idea. I'm kind of sloppy and I don't often do it, but for this circuit it's actually a pretty good idea to turn off the power while you're rearranging the wiring, because that is how, if you break the op-amp feedback loop, then the op-amp output will be stuck at either +9 or -9 or close to it. And that's the situation that gets a huge amount of power run into the speaker, or in this case it would be into the capacitor. So it's actually a pretty good idea to kill the master power here while you're messing with the wiring. Hearing the click of the speaker when I unplugged the feedback loop from the op-amp reminded me of that. So I'm going to re-enable the power, and then I'm going to go over to wave gen, and I'm going to click run. Now listen to this. Oh, that sounds so nice. It's a nice, smooth sine wave. It's almost like a flute, like a wind instrument, a woodwind instrument. Okay, and now, oh, look at that. Oh my gosh, look how beautiful that is. We have the same waveform now on the input and the output. You can see the yellow and the cyan blue waveforms overlap one another almost perfectly. So the op-amp feedback is causing the signal sent to the speaker now to look exactly the same, well, the signal coming out of the push-pull to look exactly the same as the input signal. So remember, we did that by moving this. Well, let me show you where that connection is. There used to be a wire from pin 6, the op-amp output, back to pin 2, the inverting input. Instead, now there is a wire from, you can't really see where this goes, but I just picked an empty slot here, empty hole where the emitters meet. So somewhere up here where the emitters meet, and this blue wire is going back to pin 2 of the op-amp. That's the inverting input of the op-amp. And it sounds a lot better. Now, let me show you the really neat thing to look at now is I didn't connect an additional scope channel yet to this. But if we look at this wire, we can see what is the op-amp output doing to cause that to happen. And when we see it, it will make sense. So let me just set that up. Okay, cool. So now we have scope channel 3 monitoring the op-amp output over here. And what is it doing? It's actually really amazing what it's doing. It seems so smart. So basically, the output of the op-amp, oh, first of all, okay, let me just remind you. So I took scope channel 3 and I plugged it into pin 6 of the op-amp so that scope channel 3 is looking at the op-amp output. Okay, so now feedback, through the magic of op-amp feedback, the op-amp output asks itself, what do I have to put here so that what comes out over here at the emitters matches the input, right? Because it wants to make these two things equal. And you know, because of this diode drop, so during the time when the NPN transistor is on, what comes out of the emitters here is a diode drop below this base. So in that case, it has to put out something which is up here, such that after the diode drop, it winds up back at the original blue curve. And then, then you know that when the PNP transistor is on, the emitters will be a diode drop above the bases. Well, yeah. So then the op-amp output, right, because this transistor will be off, this transistor will be on, and the PNP transistor, its emitter is a diode drop above its base when it's active. And so then the op-amp output will be a diode drop below the input signal, so that after the diode drop, it comes back to the original blue curve. Well, blue curve here, it's the yellow curve over there. So you get these little vertical spots. There's a little vertical spot in the op-amp output, and that vertical spot basically undoes this horizontal spot. It's kind of amazing. You think, how could it be so smart? And so I turned down the amplitude so it wouldn't be quite so noisy. So let me go back. It looks more dramatic, actually. It looks much more dramatic at a low amplitude. But let's go back to the 2-volt amplitude. So this is 1-volt amplitude. Let's go back to the 2.5-volt amplitude. Okay, and then we go back to the scope here. Yeah, so you see, you get this little vertical spot. This is the op-amp output pin 6 in purple or violet, magenta. And then it drops down, and it goes up, and it drops down, and it goes up. And those are exactly the places where we used to have the flat spots, but the flat spots are gone. So the horizontal spots in the push-pull output are gone because op-amp feedback got rid of them by instead putting vertical spots in the output of the op-amp. You think about that for a minute. You have to puzzle through it, but it's really cool. Okay, so I believe that's it for part 1 of lab 15. Yeah, so I'll end that with a nice pleasant 262 hertz middle C. I changed the horizontal scale to 1 millisecond per division. I changed the frequency to 262 hertz. Yeah, the miracle of op-amp negative feedback. So it will undo, feedback will do its best to undo whatever crazy thing you stick into the feedback loop, such that these two inputs match. And you can, not only can you see, you can hear the difference.